Yo, 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 time to get funky and do some math, do some linear inequalities. Let's go. All right. So, a little background. To solve an inequality means to find all values of x that make the inequality true. Just like solving an equation. Usually you have finite solutions. Like when we solve a quadratic, we get solutions like x could be 1, or x could be 2, or x could be 1 plus or minus I root 3 over 2. Right? Just two solutions in each of my examples. When we solve inequalities, a lot of times we're going to get a solution set that's infinite, like all the numbers greater than 1, all the numbers between 0 and 10. So the set of real numbers that work is called a solution set, and all the points on the number line that represent a solution set is the graph of an inequality. So these graphs are going to look like lines with certain parts shaded because we're going to start off with just one variable inequalities. It's bounded if the line segment does not approach infinity or negative infinity. So that means when you graph it, it looks like a line segment. That means it's bounded. It has boundaries on both ends. If it goes on forever in one direction or the other, so the graph looks like a ray, like x is greater than 1, that would be an unbounded solution. A bounded solution would be like x is in between 5 and 6. So when you graph it, it looks like a line segment. So first, let's relate it to interval notation. So let's write inequalities and sketch the graph and determine if each interval is bounded or unbounded. So this as an inequality right here would be all x values greater than negative 6 but less than or equal to 0, because this little bracket here indicates it's all the numbers up to 0 and including 0, and the parenthesis means it's everything right up to negative 6 but not including negative 6. So as a graph, you'll have an open circle on negative 6 and a closed circle on 0, and you'd shade everything in between. And because that graph has two boundaries on either end, 0 and negative 6, we're going to say it's bounded. Now here, whenever you see infinity in 1 or negative infinity in interval notation, it means it's going to be unbounded. So this is x is greater than 7. So it's everything starting at 7, not including 7, greater than 7. So the graph would look like that. And this would be unbounded. Alright, so solving a linear inequality is just like solving an equation, but we have to remember to flip the sign when dividing or multiplying by a negative. So, now one thing I do to make sure that I never have to flip a sign is to just get x over on the side where it'd be positive anyway. If you're someone who likes to have x always on the left, then you have to remember to divide by a negative. But you can avoid this if you just always bring x over to the side where it would be positive. So since we have 3x here and 2/7 x there, we have the greater x on the right, so we're going to move everything to the right if you want to avoid dividing everything by a negative. But the first thing I'm going to do, I see fractions, so I'm just going to multiply everything by a positive 7. So I don't have to worry about flipping the sign if it's positive 7. I'm just going to multiply everything by 7 to get rid of that 2/7. So I get 21 minus 2x is greater than 21 minus 35. Oh, forgot an x there. Too busy making 21 Savage references. So now, like I said, I'm going to bring the 2x over to the right. Alright, this is basic stuff. So we got 23x over here. And then my left hand side stays, and I'm going to, because I'm adding, you can add or subtract negatives. Doesn't matter with respect to flipping the sign. Alright, that cancels out, and we get a 56. And then divide everything by 23, and you now get 56 over 23 is greater than x. And that is, if you sound like Yoda, you would, put the subject at the end of the sentence, like, oh, 56 over 23 is greater than x. Usually, that's an awful Yoda reference, my bad, but it was forced, I'll admit it. But we like to talk like normal people and put the subject, what we're talking about, x first, and then say, oh, that's less than 56 over 23. So if you switch sides with x and the constant, then make sure you flip the sign as well. All right, now let's look at some compound inequalities. So actually, I lied, jumped the gun a little bit. Let's talk about why we flip the sign when multiplying by a negative. So let's experiment with these two. Let's first take this one on the left and multiply both sides by a negative, but not flip the sign. All right, so just want to make a disclaimer. I know this is wrong, but I'm going to show you why it's wrong. Now, if we just add x over to the right, leave the sign the way it is, and add x to the left, now we have x is less than y, when before x was greater than y. What? How'd that happen? Because we didn't flip the sign. If we did flip the sign over here, so now this is going to be correct, we divide by negative. Oops, we flip the sign. What's going on? Something happened. Oh, boom. Flip the sign, flip the sign. Now that's right. All right, here's another thing to look at. So we know 1 is greater than 0 on the right, but if we divide or multiply, doesn't matter, both sides by a negative, now we get -1 is greater than 0. That is not true. That's why you have to flip the sign. Alright, that's a smiley face. Yeah, that didn't make it much better. Alright, now let's look at compound inequality. So there's kind of two types. You got a bounded one, where you got constants on both sides, and we're going to solve this by whatever we do to the middle, we're going to do to the first and last number. So we want to try to get x alone. So I'm going to do that by subtracting 13 from the middle, from the left, and from the right. So now we get -21 is less than -2/3 x is less than 27. Alright, now we want to get rid of that -2/3 x. So we're going to multiply everything by -3/2. So we get -3/2 times -21, but we just multiplied by a negative. Both sides are, 3 parts of the equation by a negative, so we have to flip the sign. So we flipped it, and now we got x here, flip that sign, and then 27 times, I don't know why I did that, erase that, 27 times 3/2, -3/2. Alright, now we have x is less than positive 63/2, but greater than negative 81/2. Now, it's never really nice or polite to write the greater number on the left and the lesser number on the right when we write an inequality. So now we're going to just rewrite it in reverse. So we put the 81/2 over here. We still have the alligator eating the x just like it is over here. But since x is on the other side, we face it the other way. And then is less than 63/2. Alright, so those are all the numbers that if you plugged it in there would work. And this is bounded, because on a number line it would look like this. You'd have boundaries on either end. Actually, I lied, it'd be open circles, and then a line connecting them in between. Alright, let's look at one more compound inequality. So something like this would be unbounded. We have two inequalities, so like ages that, like something that would be a compound inequality like this would be like ages where it's appropriate to wear a diaper. Like when your age is less than, I don't know, like 3 when you stop wearing a diaper, 4, 5, I don't know, some of us 10, 11, or greater than like 70. Sorry for such a crude example, but it's the first thing that came to mind. So sometimes you have inequalities that are unbounded, go in opposite directions. Or like, probably a better example would be ages where you're not in high school. So like x is less than 13, x is greater than 18. So that's what we have here. This is what you would use it for. So we're just going to solve them both separately. So on the left side, you're going to multiply both sides by 5, and then add 3 to both sides, and then divide by 2. So you get it right. X is greater than 33 over 2. And then over on the right, we could subtract 4 on both sides. So we get a 0. And then be careful, you're dividing by a negative. I mean, you could just add 7x to the right side, or you could divide by a negative. Just if you divide by a negative, make sure you flip the sign. And now you'll see our solution set is all numbers less than 0, or a number greater than 33 over 2. And that's what the graph would look like. All right, and as a interval notation, it'd be all numbers from negative infinity to 0, exclusive, union 33 over 2 to infinity. All right? And now, absolute value inequalities. So, the absolute value of x is less than a if and only if x is in between a and negative a. So, like, for example, let's say the absolute value of x was less than 3. That's the same thing as saying x has to be between 3 or negative 3. Just think of like all the numbers that would work over here. Like if you plug in negative 2, that would work because that's in between negative 3 and 3. Or also the absolute value of that is 2, that is less than 3. 0 would work, but something like 4 would not work because the absolute value of 4 is greater than 3. So when you're having trouble with these, I find it helps to just like plug in some numbers or just memorize these definitions. So like if the absolute value of x is greater than a, then that means x has to be greater than a, or x has to be less than negative a. And this all applies if these are like less than or equal to's, then it's the same exact rule. So we're going to use that to write absolute value inequalities from word problems. But first, we have one given to us. So solve the inequality and check with a graph. So when it says solve the inequality, it wants you to write it without absolute values. So this is saying all real numbers within 5 units of 3. So if you think about it that way, you could think, all right, well that's like 3, 4, 5, 6, 7, and then anything less than 8, or 2, 1, 0, negative 1, negative 2, well, anything greater than negative 2. But, so that's how you can kind of interpret it with words. But if you just kind of apply the rule on the previous slide, and we say, all right, well, if the absolute value of x is less than a, that means x is in between a and negative a, like right here, this top rule. So now we can rewrite this inequality as, all right, x minus 3 is less than 5, but greater than negative 5. Once you do that, then it becomes one of the compound inequalities we did earlier. And now you see, oh, it's all the numbers between negative 2 and 8. Alright, now, where would this section be without word problems? So, word problem, or absolute value inequalities are great for describing like a range of values, like a range of like healthy weights should be within like 10 or 20 pounds of like a certain weight based on different things, you know, like your age, your height, stuff like that. That's all, like when you're looking for a range of values, like greater than or less than a certain number. So here we have, I made this word problem, we got, so using units of latitude, so the equator is at 0 degrees, the tropics are between 23.5 and negative 23.5 degrees, the temperate zone is between 66.5 degrees and 23.5 degrees, or same thing in the southern hemisphere, and you can read the picture. Alright, so what if we wanted to find an inequality that expresses north of the tropics and the southern hemisphere? So in other words, we want to express all latitudes north of the tropics, so greater than 23.5, and all x values less than or equal to 0. So the key here, when you're trying to rewrite this as an absolute value inequality, is once you set up your compound inequality, find the midpoint of these two numbers, the a in the definition. So, in other words, we want to find the middle of 23.5 and 0. So, that would just be 23.5 plus 0, which is 23.5, divided by 2, and that's going to be 11.75. Once you get that number, you're going to subtract it on both sides so that you get the same number on the right side. So 23.5 minus 11.75 is going to be 11.75. And then when you subtract it on both sides here, you get x minus 11.75 is less than 11.75. Now we have it in this form where like we have the same value of a on both sides of the inequality except one's negative and one's positive. And like our variable x is the same. We have the same expression, x is minus 11.75, x minus 11.75. So now we could rewrite it in absolute value notations. We could just go backwards and say, all right, the absolute value of x minus 11.75 is greater than 11.75. So in other words, it's 11.75 degrees within, like greater than the latitude 11.75 or less than it. Alright, we'll do more of these word problems in class, but at least now you got one under your belt. I hope you found this video helpful, and I think that's the last slide. Let me double check. Yep, it is. Alright, so have an awesome day, and I'll see you in class.